A very good morning, warm welcome to you all for the session on dual nature of radiation and matter. See, in this we are going to see a little more detail on work function again. See, already as I told, I want to take both work function and de Broglie hypothesis, but the work function itself, it's have a lot of questions to discuss. You just go through on all the questions. See, for your competitive exams, you are having both work function and de Broglie hypothesis. Now, we just concentrate about work function on this one. Next one, immediately, I just try to cover all the problems at one stretch on de Broglie hypothesis. Okay, we just go for the problems directly now. On this session is about again the same work function. See here, sodium and copper have a work function. They have given the value 2.3 and 4.5 electron volt. Then the ratio of the threshold wavelength. So they are asking about the wavelength ratio here. First one, see what you mean by work function. Again, I'll tell you here, work function is nothing but it's an energy that required to remove the electron from the metal surface. Similar one, see, this is about the energy. How you can mention here is, this is about the energy you can, that is about the photon energy. E is equal to h nu, and nu here is c by lambda, so hc divided by lambda. This one will be equal to that work function. So I just mentioned here work function w equal to hc divided by lambda. Now this one you can mention here. From here, lambda is equal to hc divided by w. See here, h is a Planck constant, c is about velocity of light. From this one, lambda is proportional to 1 divided by w. See, the same one I can mention here, lambda 1 will be equal to, will be, or even a proportional to, you can mention in any way, proportional to 1 by omega 1. And similarly I just mentioned here, lambda 2 is proportional to 1 by omega 2 here. So what they are asking in this one, so lambda 1 divided by lambda 2. So that one I just mentioned here, 1 by w1 divided by 1 by w2. So what you are going to have here is 1 by w1. See here, again you are going to have here is w2 divided by w1. W2 value already they have given, that is about, see, you can understand over here. So already they have given, this is w1 and this is w2 here. So from here you can substitute the value. So w2 here is 4.5 and divided by 2.3. This is like approximately 2 times 2 into 2 means, you can mention this one as 2 times 2 divided by 1. So from this one, answer here is 2 is to 1. So answer in this case is, a graph is drawn between stopping potential, which is in y-axis. Stopping potential in this case, see, the additional potential which has been given to the metal to avoid the removal of electron by the external kinetic energy or even external potential, that we call it as a work function. And the incident frequency what they have given here is x-axis. See, stopping potential means we have to mention this one work function in negative sign. Remember this one. And incident frequency is along x-axis, and the intercept on x-axis is a frequency. So what they have given, 0.5 into 10 to the power 15 hertz, and the kinetic energy of photon emitted from the metal when the energy of incident photon here is 5 electron volt. That is, the incident photon value here is 5 electron volt. Let me draw a graph and then I will show you. See, first here, this is along y-axis, and here I just mention along x-axis here, and y-axis they are mentioned about a stopping potential. So this is potential, stopping potential here, and the x-axis about frequency which is in hertz, and stopping potential which is in volt, right? And this is OA. Now you just consider an intercept, you just consider a point OA here. In this case, now I just mentioned here, in this case what they have given, the frequency here is 0.5 into 10 to the power 15 hertz. Now what they are asking here is, in this case they are asking about when the energy of incident photon is 5 electron volt. So what is the kinetic energy? Kinetic energy, in this case we have to find out what is the kinetic energy when the energy of incident photon is 5 electron volt. See this one already, you know this one, I just mentioned here. Kinetic energy, that is kinetic energy maxima, will be is equal to, so this is about photon energy plus W, that is work function. Here is stopping potential, so that I just mention as W naught. So what you are going to mention here is E is equal to yeah, this one E minus H nu naught, that is about stopping potential, that is here is K maximum. Now from this one, see you just substitute all the values. This one what they are asking here is kinetic energy of a photon emitted here. Now this one here is E is equal to that what they have given, that is 5 electron volt minus of, see I just mentioned here 5 electron volt minus of 6.6 into 10 power minus 34, that is about a photon H value, Planck constant, into here is a new frequency already they have given, 0.5 into 10 to the power of 15. See what you are getting, that energy which is in joule. Now you are going to convert this one joule into electron volt. So I just mentioned here 1.6 into 10 to the power minus 19. Now you just cancel here. In this case this is 10 power minus 34 and this is 10 power 15. What you are going to have here is, see, 5 electron volt minus 6.6 into, so 15 will go, that is 10 to the power of minus 9 is there, and here is 0.5, here is I just mentioned as 1 by 2, so that you can cancel here. This is 3.3, see, whole divided by, this is 1.6 here, and into multiply here is 10 to the power minus 19. Now you just cancel this one, this is 10 to the power minus 10. See here, this if you cancel here, 2 into 2 is, that is 3.3. See this one if you cancel here, 1.6 into this one, that is 3.2. So 2 times I can mention here. See from this one, what are the things you are going to have here is 5 electron volt minus 2 electron volt. So answer in this case, answer here is 3 electron volt. Interesting problem. See here, a photon incident on a metal, a photoelectric work function they have given, and produce a photoelectron of maximum kinetic energy. See work function they have given and the kinetic energy they have given. What they are asking here is wavelength associated with the photon. See, with the help of kinetic energy and work function, you can easily find out what is the energy of a photon. E is equal to h nu. See, energy of photon, now you just substitute the value in case of E. So E is equal to h nu here. In case of E, you just substitute the value. From this one, h nu here is E divided by lambda. So lambda is equal to hc divided by this one E value. Now you can easily find out. See, I will tell you here what is the formula here in this case. See, for this one, energy of photon, I just mentioned here, energy of photon will be equal to, that is E, I just mentioned here, E will be equal to kinetic energy maximum, that is kinetic energy I just mentioned here, plus work function. In the previous one, kinetic energy maximum means this W will come over here. See, from here the W will come here. So this is the concept. See, last we have seen the same kinetic energy is equal to energy of photon minus W is there. Yeah, the same formula we are using. According to this, see, according to this, how we can find out here is, they have mentioned here kinetic energy value here is 3 electron volt, plus work function they have given 2 electron volt. So what you are having here is 5 electron volt. Now wavelength, how you can find out the wavelength here is, according to energy of photon, E is equal to h nu. Again I just mentioned here hc divided by lambda. From this one, lambda is equal to, lambda here is hc divided by E here. Now, I just mentioned here, substitute the value, lambda is equal to h here is 6.6 into 6.624 into 10 power minus 34. Now I just mentioned here 10 power minus 34 into 3 into 10 to the power 8 and whole divided by volt divided by what we got, the energy value here is 5 electron volt. Now this one, in this case, 5 electron volt. See here, electron volt already they are mentioned here. In this case, see, you just substitute the value. Now you just cancel this one. Here is approximately 1 is there, 1.3. Now you just cancel this one. From here, what you are going to have here is C, and even you have to mention this one. This is an electron volt, so you have to mention here, convert this one in joule so that you can get the answer. So 10 to the power minus 19 here. Once you simplify this equation, this 19 cancel here, and then with the 8, once you are going to cancel this one, see, you can easily cancel over here. See, what you are going to have here is 3.9 will come again. You can cancel with this. This is a 1.2 will be there. So approximately what you are going to have here is 2400 angstrom. You just confirm here 2400 angstrom. From this one, which is very nearer to here, is 2480. So answer here is this one. See here, yeah, this questions with a small assumption even you can find out here. A photo cell is illuminated by a small bright source placed 1 meter away. Now I just mentioned here, for example, this is a photoelectric. For example, like a cell mirror, like a solar panel which has been placed in the sunlight. This is a photo cell which has been placed in the light. I just mentioned here, this is the light. See, this one I just mentioned here. For example, this is the light which is at the distance here is, for example, 1 meter away. The same one, second case, what they have mentioned here is, in the second case, the same light which is going to place just half meter away. See, first one here is 1 meter. Now this is long distance. Now little half of the distance is going to close. So that what happened here is, the number of electron emitted by the photocathode would be, already you know this one. See here, if the intensity is increases, so what happen here is, if intensity is increases, the power which can be generated by the solar panel will also increase. How much factor? See, from this one factor, definitely it's going to increase as you are going to decrease the distance. So these two only possibilities are there. These two no possible, because it won't decrease, only it will increase. For this one, see here, I just mentioned here, in this case, intensity I is proportional to, or even what you mean by intensity, we can mention here, the power, particular power which can be exposed to the particular area. That is about intensity. See, you just consider about the area, how much amount of power which is covering this area, that is about the intensity. For this one, this is about the power of the source P here, and the intensity I just mentioned here, 4 pi r square. Now from this one, see here, in that case there are two things. One is about I1 here. Now I just mentioned here, in this case, see, I1 which is directly proportional to, what are the things will be there, this is P. See here, in this case only you can understand here, from this one, see, I is proportional to, here I just mentioned here, I is proportional to P divided by R square. Now in that case, here what I am going to mention here is, I1 is proportional to P1 divided by R1 square, and already I, which is proportional to, if intensity is increases, I is proportional to number of electron. So I1 is proportional to N1. So in that case, I1 is proportional to P1 by R1. Similarly, I2 is proportional to P2 by R2 square. Now, what they have given here is, I just mentioned here, I1 divided by I2 will be equal to, see, P1 divided by R1 square and P2 divided by R2 square. From this one, P1 by R1 square P2 into R2 square. See, I1 by I2 is this one. Now, similar I1 by I2, instead of that one, I just replace into N1 by N2. See, what they are asking here is the number of electron emitted by photocathode. So, N1 by N2 here is, now you just mention here, power will be the same. So, in that case, already they are mentioned here. See, you just go through on this one. See, when the same source of light, so power will be the same. So power will be the same in this case. See, P and P will be cancelled here. From this one, here is n1 by n2 here is r2 square divided by r1 square. First one they have mentioned here, that is 1 meter here, 1 meter. Second one they have mentioned here is half meter. So both are square here. Now you just mention here 1 by 4 divided by 1, that is 1 by 4. So n1 by n2 here is n1 by n2 here is 1 divided by 4. So what they are asking here is the number of photoelectron emitted by, as the distance has been increases, the number of photon has been emitted here. See, once you are going to increase the distance here, changing the distance, this is n1 and this is n2. Here you are not going to increase, you are going to decrease here. From this one I just mentioned here, n2 is equal to, see here, this one, n2 is equal to 4 times of n1. So that factor which can be increased by 4 times. So answer here is problem. This is also quite interesting. You just concentrate here. See, the threshold frequency of certain metal is V naught. See, first one, what you mean by threshold frequency? See, this is about the threshold frequency is a particular frequency or the minimum frequency at which what happen here is that the electron that can be easily emit from the material. See, at a particular frequency, say for example, if it is 10x is more than enough, so that the electron will be emit out from the metal surface. So that 10 is threshold frequency. Suppose if you are having 5 frequency, means that is not sufficient. If you are having only 10, that is about threshold limit or even a threshold level where you can emit the electron from the metal surface. So in that case, so see here, nu naught is the threshold frequency. Now when the light frequency here is 2 nu naught, now incident on the metal surface, see here, I just mentioned here. See, first you just consider a metal surface. This is about the metal surface. On the metal surface, one light frequency of nu naught is more than enough, so that the electron will be emit out, eject out. Now this one, instead of nu naught, what they have given here is 2 nu naught. Now it's going to incident on this one. So the electron which is coming out here, so electron which is coming out from this one, that values will be, see here, the electron which is coming out from here with velocity here is 4 into 10 power 16. If the frequency is incident on 5, instead of 2 nu naught, 2 nu naught here is 4 into 10 power 6. Suppose if it is 5 nu naught, means what is the free velocity of the electron, emitted electron? See here, nu naught is a threshold one, so electron will come out. If it is 2 nu naught, means velocity here is 4. If it is 5 nu naught, means what is that velocity? That's what they are asking here. For this one, see here, first one, similar here, kinetic energy here is, so for the first case I just mentioned here, 1 by 2 m v1 square, that one will be equal to, so the emitted energy photon frequency value they have given 2 h nu naught, right, minus what you are having here is initial threshold value here is h nu naught. See, from this one what you are having here is h nu naught. Next one, see the same one, 1 by 2 m v2 square. This is about the kinetic energy here is what they are given 5 h nu naught. In this case, the threshold energy here is h nu naught. So what you are going to have here is 4 h nu naught. Hope you can understand here. See this one, this is 2 h nu naught. See here, this is 2 h nu naught, that is for this one, right? For this one, h nu naught is nothing but this is like what you say, photon energy, right? And this one here is a threshold photon energy. This is 5 this one, this one 5 nu naught energy, and this one is threshold one. See, from this one what they are asking here is v2. See, what I'm going to do here is, see this one, I just mentioned here, I just write on here. See, from these two equation, this one I just mentioned as equation number 1, and this one I just mentioned as equation number 2. From equation 1 and 2, see here, uh, 1 by 2 m v2 square is equal to, from second equation I just take it here. From second equation, 1 by 2 v2 square here is 4 h nu naught. Instead of h nu naught, what I'm going to do here is 4 h nu naught, already you know this value, that is 1 by 2 of m v1 square. Now you just cancel here, nu 1, this is v1 here, velocity, and even m and m will be cancelled here. So v2 square is equal to, see here, this is 2 times here, or even 1 by 2 if you cancel here, v2 square is equal to 4 into v1 square. So again v2 is equal to 4 times of v1. v1 value already they have given. v1 value here is so this one, if you are taking this one 2, so from here this is 2 into v1 value here is 4 into 10 power 6 meter per second. From here answer here is 8 into 10 power 6 meter per second. So answer in this case, see here, in a photoelectric cell, current stops when a negative potential of 0.5 volt is given to the collector with respect to emitter. See here, negative potential if you are going to give from collector to emitter. See here, I just mentioned in this case, see this one, for example, this one is about collector and this one is about emitter. From the emitter, you see, whenever the light is passing through here, it will emit the electron. At the same time you are going to give the potential over here, so that what happen here is the electron is fastly moving over here and it will be here and it will be attracted to the cathode. See this one, this is about collector here. See, from this one, in this case, what they are going to do, see, actually what you are having here is you are having some parts positive potential because of this one. Say for example 0.5 or 1 2 3 like that you are going to give, but you are going to give negative potential minus 0.5 volt. If you are going to give, what happen here is the maximum kinetic energy. See here, this one kinetic energy maximum, that one will be equal to what you are going to give that potential in electron volt. So here both are same. Whenever the potential, see here, whenever the potential, the negative potential which is having a capability to stop the electron here is, that is about they are mentioned here. See this one, I just mentioned in this case. See, this one will be equal to 1.6 into 10 to the power minus 19 into potential here is 0.5. So what you are going to have here is zero point 0.8 into 10 to the power minus 19 joule. See, this is the electron volt. Now you have converted into joule. So kinetic energy maximum in this case, answer here is the next problem. The work function of potassium. So they have given W value. When it is illuminated by wavelength, they have given 3300 angstrom. Photoelectrons are emitted. The stopping potential, see here, the stopping potential of photoelectron here is, so what they are asking here is stopping potential. And this one here they have given the Planck constant. Usually they won't give, but they have given here. In this case, 1 electron volt value and this one C value, all they have given. See, first in that case, see here, already you know this one. This is about stopping potential. In this case, I just mentioned here. So E is equal to work function W naught plus this one kinetic energy maximum. See here, kinetic energy maximum in this case. See, kinetic energy, that one will be equal to this is in joule. They have given in a electron volt. See this kinetic energy is like this one, uh, the amount, say the minimum energy that required to remove the electron from the metal surface, that is about the work function. When you are going to give this potential, this much 2 electron volt of energy, once you are going to give, that will produce the work functions to remove the electron, so that one will be equal to electron volt. See here, so this kinetic energy will be equal to an electron volt. So I just mentioned here, this one, the energy which is in joules here, and these two are in electron volt. See, work function and this one kinetic energy maximum, that is about electron volt, already they have given. So that is in electron volt only. See, from here, now I just mentioned here, HC divided by lambda equal to H nu equal to C by lambda. From this one I just mentioned here, work function W naught, and this one here is EVS. Now from this one, H value here is 6.6 into 10 power minus 34, and the C value here is 3 into 10 to the power 8, and here whole divided by, now this one, whole divided by lambda value here is 3300, angstrom is 10 to the power minus 10. See here, 1 electron volt is equal to 1.6 into 10 to the power minus 19 joule. See, from this one, 1 joule is equal to 1 divided by 1.6 into 10 to the power minus 19. See here, in this case, what they are given value here is in a joule. Now you are going to convert this one in electron volt. So what you are going to have here is, see, I just instead of 1 joule, see here, instead of 1 joule, what I'm going to do here is I just going to divide this one by, see here, 1.6 into 10 to the power minus 19. Now from this one, see here, you just add these together. See, if you cancel this one, this is double zero, this 2 0 you can cancel here, that is for 6 times here. See, from this one, this is 11, you can cancel again here, that is 111, this is see here, 6.6, that is 0.6 here. See, from this one you just cancel here, this one will be equal to, so this one here is W naught, that is they have given 2 electron volt, plus this one kinetic energy we are going, that one only we are going to find out, that one I just mentioned here, Vs. Now from this one you just cancel this one. See, what you are going to have here is see, it's 10 power, see, remaining thing I just write on here, 0.6 into 10 power minus 34 into 34 into 10 to the power 6, and whole divided by, this one here is 10 to the power 10, and this one minus 19, here is 10 power minus 29. This 1.6 I just write on as 3 by 2, so that you can cancel here, this is for zero point 0.2 times, and even you just take this one for 0.4, so approximately 0.4. In that case, what I'm going to mention here is, see here, this is 2 electron volt plus Vs. See, from this one I just mentioned here, this value here is 3, approximately 4 means 3.75. If you cancel this one, you will get here, that one will be equal to 2 electron volt plus this one Vs. From here, Vs equal to, so what you are going to have here is 3.5 minus 2, here is 1.75 volts. So answer in this case, important, hold the question paper question. See here, photoelectric emission is observed from a metallic surface for the frequency. So two different frequencies, they have received a photoelectric emission. See here, one is about nu 1, another one is nu 2. In this case, nu 1 frequency is maximum than nu 2. If the maximum value of kinetic energy of the photoelectron emitted in the two cases is in the ratio of 1 is to n, then the threshold frequency value of a metallic surface is what? See, in that case, what I'm going to mention here is, first one I just mentioned here. Say, for example, this is about a metallic surface here. See, on the metallic surface, see, uh, see, this is about a one frequency, that is nu 1. So that what happened here is, because of the light, it emits radiation here. So this is first one, and the second one similarly like this. This is the second one, nu 2. Even that one also emit the radiation, which is having a kinetic energy. This one here is E1, and this one here is E2. So they have given the ratio of E1 divided by E2 here is 1 is to 2. And in this case, additional information what they have given here is nu 1, which is greater than nu 2. So in this case, see here, nu 1 is maximum than nu 2 here. For and additional thing, see, from this one, kinetic energy here is E1. How you can mention here is E1 is equal to, you can mention here, H nu naught. This is about the kinetic energy, that one will be equal to photon energy plus nu naught here. This is about the threshold frequency for the first case. For the second case, E2 equal to H nu 2 minus nu naught here. See, from these two equation, E1 divided by E2, so that one will be equal to H nu 1 minus nu naught divided by H nu 2 minus nu naught. See, already they have given E1 by E2 value here is, see here, that is 1 by n. I'm sorry, here this is 1 by n, so 1 by n will be equal to H nu 1 minus nu naught here. That one will be equal to H nu 2 minus nu naught. Now you just cross multiply here. Cross multiply here, what you are going to have here is H nu 2 minus nu naught. That one will be equal to n H nu 1 minus n nu naught. See, from here we are going to find out nu naught value. So nu naught value, just take it over here. See, from here n nu naught minus nu naught, that one will be equal to n h nu 1 minus h nu 2. See, from here again, see here, this one nu naught is common here. So what you are going to have here is n minus 1. Here in this case, what is common here is h is common here. H is equal to n, see here, n nu 1 minus nu 2. So from this one, nu naught value is equal to h. Here is what you are having here is h n nu 1 minus nu 2 divided by n minus 1. So answer in this case, let k1 and k2 be a maximum kinetic energy of two different photoelectrons when photoelectrons emitted when two monochromatic beams. There are two beams, both the beams having a emitting a photoelectron which is having a kinetic energy k1 and k2, and additional information lambda 1 will be equal to 3 times of lambda 2. First, I just mentioned the relationship between your wavelength and kinetic energy. See, K1 will be equal to hc divided by lambda 1, and work functions will be the same. So I just mentioned as pi, and K2 will be equal to hc divided by lambda 2 minus pi. Now, okay, now this one I just consider as equation number 2. This one I just consider as equation number 1. Additional information here is lambda 1 will be equal to 3 times of lambda 2. Next one, we are going to utilize equation number 1. K1 will be equal to K1, that one will be equal to HC. Instead of lambda 1, you can mention as 3 lambda 2 minus 5. Now, see, K1, you just multiply with the 3 here. So this is 3K1, and 3 by 3 will be cancelled here. 3, see, multiply with 3. I just mentioned here, multiply with the 3. So what you are going to have, lambda 2 minus 3 pi. Now you can rewrite this one a similar manner. 3k1 will be equal to hc divided by lambda 2 minus pi and minus 2 pi, that is 3 pi. See this one, only on based on this one, what you can mention here is 3k1, that one will be equal to, that is k2 here. From equation 2 you can mention here minus 2 pi. Again, from k2 will be equal to 3k1 plus 2 pi. See, additional information, k2 value will be k1 plus 2 pi. See, from this one, what you can mention here is, if this is constant here is 3k1 will be equal to k2. So that k2 is maximum here. So you can rewrite this one 3k1 which is less than k2, or even k1 which is less than k2 by 3. So answer in this case here is the session. This presentation and previous one completely related to the work function, and the next one which is completely related to the de Broglie hypothesis on third presentation, that will be updated in the next presentations only. Immediately you can get the updates once you just subscribe the channels, and so that you can get a frequent update on all the topics. Let me finish all the topic, and I will put a list of presentation in the description also. You just go. Okay, any doubt, you just pass your doubt on the comment sections. Thank you.